Hello all. In this session we discuss simulated annealing algorithm, which is an important local search algorithm after hill climb algorithm. In my previous sessions I covered what is hill climb algorithms. So hill climb algorithm basically helps in optimizing AA problems, where it mimics the nature of a blindfolded hill climber, how he climbs the hill with overcoming the problems. We solved some problems on that. You please go through those sessions, how we solve the problem. So hill climbing algorithm has one drawback called you cannot go back to the previous state, means we cannot backtrack. So this simulating annealing algorithms, they overcome this drawback and they give a efficient solutions. What is a simulating annealing problems, right? Annealing in metal, what do you mean by annealing? So let us see what is a physical annealing process. A physical annealing process means we use this annealing process with the metals, right? Suppose we heat up some metal until a particular temperature, means annealing temperature. This metal will melt down into some liquid form or nearby liquid form. Then we increase the temperature, and when it reaches the annealing temperature, now we slowly cool down the temperature, and while cooling down only we try to change the shape of this metal into our desired shape. Means if you want to get some desired shape, while cooling down itself only we change the shape. So when in a hot condition, molecules of this metal are they are in weaker, and when the cooling process, the molecules will become strong. The same process now we apply this analogous to our AA problem solving environment. How annealing is applied in AA solving problems. So just analogy, what is it? In a physical annealing process we use the metal. In simulated annealing, like in our AA problems, we use the metal placements. Here one optimization problem. I told you optimization means we are trying to find the best possible solution for a given problem. Sometimes we need to maximize the goal, or sometimes we need to minimize the things, so that we try to achieve our best solution. Now there, in case of it is a metal, here our problem, one optimizer problem, their energy state we calculate the means when we give high temperature melting down and we give low temperature it is cooling down. So energy is changing from higher state to the lower state. How much temperature we are giving to the metal, that is calculated by energy state. Here the same thing, it is replaced in our environment, we call it as a cost function. In physical process it is energy state. There we give temperatures to heat up or cool down. To heat up we give more temperature, to give cool down we reduce the temperature. In our AA problems we use a parameter, control parameter, something like iterations. With the help of iterations we try to solve this one. Their final product of this annealing is a crystalline structure. Here final product of our algorithm is a optimal solution. So this is most popular algorithm in local search algorithms. So here also it uses it doesn't care about the path, it wants to find the best state that matches with the goal state. So it is a random search method developed by Kirkpatrick in 1983. So it generates a random moves. So let us see how the concept. First when you try to solve the problem, first we initialize the environment, like we set the initial and final temperatures, iterations at each temperature, and while this loop will rotate, as long as your final temperature equals initial temperature is true, this will go on. Randomly introduce a small change to the problem, and we, after applying a small change, again we try to solve the problem. This one specific algorithm is given in annealing problem. Let us see a small problem that is solved using the annealing example. Let us see one mathematical problem. Find the minimum value of the function using simulated annealing. So this is one function given as a minimize this function. Minimize this means you have to find the input values for this function that gives the smallest output value after giving the inputs, means it produces smallest output value. Here we have two constraints, that here this equation contains x1 and x2 variables. So x1 falls in the range -2 to 10, my x2 falls in the range -1 to 11. Now assume temperature, as means annealing process, we give the temperature to heat up the metal and we decrease the temperature to cool down. So here the factor how much we are giving, we decide by this 0.8. The number of iterations here means control factor is 2. Now how we solve this problem, means how we find the parameters like input values x1, x2 that finds the minimum value of this function, smallest output of this function. So first step in simulate annealing process, we take a initial temperature T for random points in the solution. Let us take a 4 random values, like here 2 meant for x1, 0 means x2, 5 x1, 10 x2, 8 5, 10 10. We take population 4 random values and we substitute these x1, x2 into the equation. So when you equation you get the 4 values, like when you give 2 0 you get 476, when you give 5 10, like these are different f1, f2, f3, f4 are outputs of 4 inputs, 4 random inputs. So then we calculate 384.2, one total temperature, initial temperature. First we have to calculate by giving a random variables. Now then I have to take one design point. Design point means let us take randomly one point called x1, 4 and 5, means x1 4, x2 5. Now when you substitute this 4 or 5, you get my function output as 349. Just you keep it aside as 349. Now we have to find the, means our local search algorithm find the nearest neighbor, who suits the best, who resembles the best goal state. So now randomly I have taken 4 5. Now I make a small changes to this 4 5 by introducing random, by making one calculation, finding 2 new values. That suppose 4 5, I take 2 random number, any 2 random numbers between 0 and 1. I took 2 random variables 0 and 1, and then I changed this slightly because x1 falls in the range -2 to 10, x2 falls in the range -1 to 11. I made a small changes to these values 4 and 5, as suppose when you plus or 6 accuracy is there, means maximum it falls in the 4 plus or minus 6, means your range is around x1 falls in between -2 and 10 and x2 is between -1 and 11, based on our plus or minus 6 accuracy. Why plus or minus 6 accuracy means here these values, within these values already they have given 4 and 5. After that this much accuracy we have to work out. Now I make one equation, third step. The third step is like a we are making a slight changes to our designed input, like -2 plus u into 10 minus of minus. So these are new values, 1.72 and 5.84 are new updated values of my random designated input. Now again I apply these 2 new values. means this is a cooling system phase, means cooling down. Now here after by introducing this thing, my programming is going in a cooling down, means slight changes again reapply here. So with these new values 1.7 to 5.84 again I applied, so 349. So originally it is it gives us 387 and my designed input gives the 349. There is a difference of 38, means 38 is positive. Actually I am minimizing the function, but this is value increased. So now whether this is acceptable or not, then we calculate one function called metropolis criteria. This metropolis criteria checks whether the current input current point can be considered for further changes in the values. Means here regularly I have taken one best input and making slight changes in the input and substituting in the formula. I am trying to minimize that value. So whether that point changed value is correct or not, current point, I decided by using metropolis criteria. So this is like a probability of accepting new design is given as e power difference in your function outputs by into kt. Now here my output is like and we take one random number, we check let us say R1 random number, and we the random number divided by our in function output, this function e power delta f by kt is so it gives the value 0.9041. That means my random number is smaller than output of this probability value, then we can accept that point. That means this point is accepted now, 1.7 to 5.7. So what we do, again we reapply this 1.7 to 5.84 as inputs to my function, and I get it as a new output as 387. So what I do, again cooling down phase, again I reduce some values of these two by taking some random values and checking with the falling range. Again I change 1.72 to 5.82 and I got a new values, nearest values 6.76 and 8.60. Now this time I got a minus 74 as my difference between the outputs. So when negative value is there, it is automatically you are in a minimizing position, so it is accepted. So this process goes on until you find a minimum values and iterative. If there are no further changes in the output, then we find this one, like first we take a highest number, like increasing the temperature, and then slowly we are reducing that points and substituting in the equations, so that I find out whether it is going in a minimum direction or not. So these are accepted as final input values for which my function generates the smallest output value. So like this we solve the problem using simulated annealing. So first I have taken a randomly, I have taken a highest input, then I may use by using a probability of acceptance, like energy conversion in our annealing process. Here also using this cost function I calculated and I given a new values, and those checking of new values is done by metropolis criteria, whether it is acceptable or not. So like this, a simulated annealing example solves the problem. Thank you.